Meromorphic functions are defined as follows. So a function from a domain U inside of C, which maps into C infinity, which is the complex plane union the point infinity. So such a function is meromorphic if for every z0 in U there exists an R and a disk contained in U such that F restricted to the punctured disk there has either a pole or a removable singularity at z0. And at poles, the value of F is infinity. So this is basically a way to define a function that's analytic everywhere except possibly at isolated points where it has a pole. And at those points, you say its value is infinity. We can also define what it means to be meromorphic at infinity. So f defined on a neighborhood of infinity, as we've defined before, is meromorphic at infinity if f of 1 over z is meromorphic at 0. So now we can define functions at infinity to be either analytic or meromorphic, and then functions that are meromorphic at a point, if they have a pole, will actually equal infinity. So we've basically extended everything we do on the plane to the setting of C infinity, which is called the Riemann sphere, which we can also realize as we have with fractional linear transformations as CP1. We don't need to use this viewpoint too much, but we can if we want to. Okay, so meromorphic functions are nice because the set of meromorphic functions on a domain U forms a field. So you can do multiplication, division of non-zero meromorphic functions, and addition and subtraction. And that's the nice thing about meromorphic functions. So why is that? Well, if I have f and g meromorphic, I guess the main thing to show is that f over g has to be meromorphic. And basically, f being meromorphic means I can hit it with, well, I guess we should focus on a particular singularity. Let's say it maybe has a singularity at 0. Well, f is meromorphic, so I can hit it with a power of z to the n to make it analytic at 0 and non-zero there. And I can hit g with a power of z to make it analytic and non-zero at 0. And that's kind of a unified definition of having a removable singularity or a pole. You can do this in either case. But then that means that the function f over g times this power of z will be analytic and non-zero at 0. So you can do this at any possible singularity if you start out with meromorphic functions. And so a quotient of meromorphic functions will still be meromorphic, and it's not too hard to show that the sum of meromorphic functions is meromorphic, so you get a field out of them, which we didn't have with just analytic functions. Here are some good exercises to help understand meromorphic functions. A function that's meromorphic from C infinity to C infinity is actually rational. And another good exercise is that if you have a meromorphic function from C infinity to C infinity, if it's also injective, you can show that it's a fractional linear transformation. And from this, you can show that all of the meromorphic bijections from C infinity to itself are actually the fractional linear transformations, which justifies how we used them earlier. So meromorphic functions provide a nice unification of functions with poles or removable singularities. Now let's talk about the black sheep of the singularity family, which is the essential singularity. By our earlier characterizations of poles and removable singularities, we see that essential singularities are characterized by the fact that the function f defined on a punctured disk, which is analytic, has an infinite Laurent series expansion with infinitely many negative powers of z minus z naught. So we have to have an's non-zero for infinitely many negative n's, and that characterizes essential singularities. And that justified how we could say that e to the 1 over z had an essential singularity at 0. The next theorem, called the Casorati-Weierstrass theorem, will show us that functions at essential singularities have sort of wild behavior. So if f, and we'll do this at 0, so if f is analytic on the punctured disk centered at 0, and it has an essential singularity there, then we can show that f of this, the image of f on this punctured disk is dense in C. So the image has the property that I can approximate any point in the complex plane with points from the image here. And you could keep applying this for smaller and smaller radii. So for every little r less than big R, this image would still be dense in C. And this gives us this kind of powerful corollary that for any w in C, there will exist a sequence of zn's tending to 0 such that f of zn goes to w. So it's as far from being continuous as you could imagine, because I can find a sequence for any complex number. I can find a sequence of points tending to 0 so that the image tends to whatever point I want. So let's try to prove the Casorati-Weierstrass theorem. Okay, so if this image of f on the punctured disk is not dense, that means there's some point that we cannot approximate with values in the range. So there'll exist a point C in the complex plane such that f of z minus c is bounded below near 0, because I cannot approximate c arbitrarily closely. But then I get that 1 over f minus c is bounded near 0, and so it has to be analytic there. And since we already kind of pointed out that meromorphic functions form a field, we'll get that this will be a meromorphic function, so its reciprocal is meromorphic, and then you get that f is meromorphic at 0. So its singularity cannot be essential, and that proves the Casorati-Weierstrass theorem. This theorem does not tell the whole story about essential singularities. In fact, a big goal of complex analysis courses is to prove something called the big Picard theorem. The big Picard theorem says something much stronger, which is if I have f with an essential singularity at 0, then the image of f on that punctured disk omits at most one value in the complex plane. So not only is it dense, but it hits everything in the complex plane with at most one exception. And again, you could apply that to smaller and smaller disks. And the same thing holds on every one of these for Rn going down to 0. So on every punctured disk that's smaller, centered at 0, the image of f there will hit everything with at most one exception. And this gives kind of the contrapositive, gives an interesting characterization of having a pole or being meromorphic. So if f is analytic on a punctured disk and its image omits at least two values in the complex plane, then f has to be meromorphic at 0. So this kind of theorem, just blows our earlier theorems out of the water, but it takes a lot of work to prove the big Picard theorem, and there are several different proofs, and I hope that we will get to at least one of them.